So the question is, how would you find the zeros of p of x equals x to the fifth plus 32?
Isn't that 2 to the fifth?
Well, negative 2 to the fifth would work. That's 1. How many more are there? There should be 4 others. So how do you find them? Well, guess what? You go back, and you guys are going to love this. You go back to Trig land. Yay! I know you guys were missing trigonometry. So guess what we get to do? We get to go back to Trig land for this example. But first, let's analyze what this is asking for. How do you find the zeros of a polynomial? Well, one way to get started is to set the polynomial, the formula for the polynomial, equal to 0, right? So what we're really asked to do breaks down to solving this equation. X to the fifth plus 32 equals 0. Or if you solve for x to the fifth, another way of thinking of it is we're asked to solve this equation. X to the fifth is equal to negative 32. Another way to think about it is to find, we really just need to find the 5/5 roots of negative 32. We know that there's got to be 5 zeros from the fundamental theorem, right? It's a degree 5 polynomial. And you know that one of them you get by taking the 5th root of both sides. And so you get negative 2 for one of them. That's the real numbered answer. There's going to be 4 complex answers is what I'm trying to get at here. So what this breaks down, there should be 4 more. There should be 4 more zeros, and that's by the fundamental theorem of algebra, FTA. Okay, so it breaks down to this. We want to find the 5 fifth roots, if I could spell it right. We want to find the 5 fifth roots of negative 32. So now hopefully we understand the problem. Does everybody agree that's the issue here? How do we find these additional roots? Okay, well, I have to help you recall something. Recall. If you write a complex number in trig form, the shorthand for that, so if you have z equals a plus bi, that's standard form, right? A and b are real numbers. In trig form, it can be written as z equals r cis theta. Remember that? Where cis stands for cosine theta plus I sine theta. Remember that? Okay. Now r is the absolute value of z, which is the square root of a squared plus b squared. That's how it relates to the a plus bi form, right? And theta is the direction angle when you graph a plus bi in the complex plane. Theta is a direction angle. Okay. Does anybody remember a theorem that allows us to find the powers of r cis theta very easily when it's in trig form? Yes. R to the n cis n theta. The name of this actually has a name. This is Demois's theorem.
The power theorem.
It looks like de Moivre. That's what it's called. Well, it turns out that this theorem holds when you replace n with 1 over n, which represents the nth root. I'm not going to prove it, but this holds when you replace n with 1 over n. In other words, we could write it like this: r to the 1 over n cis theta over n. Now, I'm not calling this z to the 1 over n because there are a few representations of z to the 1 over n. Because the fact is theta is not unique, and you could keep adding. So to represent z up here, you could keep adding 360 degrees to the angle. And in fact, you could keep adding multiples of 360 because that's the period of the sine and cosine functions. So there's multiple representations in cis form. So I present this formula, but I don't actually think about it this way. I think about it this way. R to the 1 over n cis, I think of it as theta over n plus 360 times k over n. And all that's telling you is that once you find the first one given by this formula, this is the only formula you need to recognize. If you use this formula to find what I would call the first root, even though we mark it with a subscript of 0, then all you have to do to find the subsequent ones is add in multiples of 360 over n. And that will help you find all of them. So I know right now it's all a blur what I'm talking about because you need to see an example to make it make sense. Find all 5 zeros of x to the 5th plus 32 equals 0. So really, when I say find the zeros, we're talking about p of x is defined as that polynomial on the left side. And i.e. find the 5/5 roots of negative 32. Okay, first thing we have to do is convert negative 32 to cis form. So, okay, so z equals negative 32. If you graph z equals negative 32 in the complex plane, you'll see how to convert it to cis form without using the formulas. So remember, in the complex plane, the horizontal axis is the real axis, and the vertical axis is the imaginary axis, we'll call it. But negative 32 is over here on the real axis, right? So we need an r and we need a theta to put this in r cis theta form. What is r? What is the distance that negative 32 is from 0? 32. So r is the absolute value of z, which is positive 32. The absolute value of negative 32 is positive 32. What's the angle? You can see, without using the formula tangent theta equals b over a, you can see what the angle is. The angle is 180. Theta is 180. So z in trig form, you're going to have to convert to trig form. Z in trig form is positive 32 cis 180. Does everybody see that? And which stands for 32 times the quantity of cosine theta plus I sine theta. Does everybody see that? Now let me show you how easy this actually is. All you need to remember is the original formula I showed you for z to the n, which is r to the n cis n times theta, which is the one you memorized before the last test. And then remember, oh, I'm finding roots. So one value of z to the 1 over n, so one value of the nth root of z is r to the 1 over n cis theta over n. So if you remember that formula from before the first test, you can derive the formula you need to use to find these roots that you're looking for. Okay? In this case, what is n? It's the 5/5 root, so n is 5. Okay? So let's find what I'm going to call, I'm always going to call that first root the root you get. So this guy, this particular one gives you the first root w naught, w subscript 0 we call it. Okay. So let's fill it in. 32 to the 1/5, right? 32 to the 1/5, which is 2. Cis, okay, what's the angle? 180 over 5. So does everybody see I'm just filling in this one and only formula you need to memorize? Or derive from the original version of de Moivre's theorem. Does everybody see that's what I'm filling in? Okay, so let's simplify that. So that means W naught is 2 cis, what's 180 divided by 5? 36. 36? Okay. Now that's just one of them. There are 4 others, right? So that little talk I was given that you probably didn't quite, it probably wasn't quite clear. It never is the first time you hear it. You can get the others by adding multiples of 360 over n. That's the trick. But that's just going to be 360 over 5 added consecutively. What's 360 over 5? So 360 over 5 is 72. So if you add in multiples of 72, you'll get the other zeros. Add in multiples of 72 degrees to get the other zeros. Before I answer your question, let's go ahead and finish this up. To get other zeros. Okay. So, well, that's easy enough. So what I would call W1 would be obtained by simply adding 72 degrees to 36. So what does that give me?
108?
Yeah. And if it's a particularly difficult thing to add, here's a cool way to do it on your calculator. So we could figure out how to add 72 because you just add 70 to each one and then add 2. That's easy enough. But let's say we're a difficult one. So where are we starting at? We're starting at 36. In your calculator, enter 36 and then go plus 72. And there's the 108. And then just keep hitting enter and it'll keep adding 72 and get you the other ones. Okay? So not that we needed it for this one. If we think real hard, we add 72, we'll get 108. So how did I go from this angle to this angle? I added 72 degrees. Okay, and then we only have 2, so we have 2 more. W2 is going to equal 2 cis. If you add 72 to 108, what do you get? 180. Is that the one we already knew about? That's negative 2. 2 cis 180 is negative 2. Okay. And then we have one more. So we added 72 to get to the 180. And we'll get the last one. Oh, wait. No, I'm sorry. I was thinking we only had 4. We only have 3. We have 2 more to do. So W3 is the second to last one. 2 cis, add 72 to 180. What do you get? Not 152, but 252. So add 72 again. And then W, since we started counting at 0, W4 is the 5th root. So W4 is 2 cis, add 72 again. What do you get? 324? Okay.